lecture will be over section 28.5. We're going to be looking at X-ray production and scattering. So when rapidly moving electrons that have been accelerated through a potential difference on the order of 10 to the third or 10 to the sixth volts, strike a metal target, X-rays are produced. In Compton scattering, X-rays strike matter. Some of the radiation is scattered with a longer wavelength than the incident radiation. And the increase in wavelength, or delta lambda, depends on the angle through which the radiation is scattered. So you can see here you've got the incoming photon, you've got the scattered photon, which has a different wavelength than what's coming in. And then you've got the recoiling electron after the interaction that goes away with a certain amount of momentum, p sub e. This is the kind of stuff that you will see whenever if you ever get the chance to go into X-ray or even CT, because this is the kind of thing that this phenomenon is what you're going to see in those applications of physics to medicine. So X-rays were first produced in 1895 by Wilhelm Röntgen. Using an apparatus similar in principle to this, electrons are boiled off from a heated cathode by thermionic emission and are accelerated towards the anode. By a large potential difference, the bulb is evacuated to a residual gas pressure, so the electrons can travel without colliding with air molecules. When the voltage is a few thousand volts, a penetrating radiation is emitted from the anode surface. So you can see that coming off there. Because of their electromagnetic origin, it is clear that X-rays are electromagnetic waves. And like light, they are governed by quantum relationships. So you can talk about X-ray photons or quanta, and the energy of the X-ray photon is related to the frequency and wavelength in the same way as it is for other photons. Typical X-ray wavelengths are anywhere from a thousandth of a nanometer to 1 nanometer. X-ray wavelengths can be measured quite precisely by crystal diffraction techniques, which have been discussed previously. X-ray emission is the inverse of the photoelectric effect. Photoelectric emission, the energy of the photon is transformed into the kinetic energy of the electron. In X-ray production, the kinetic energy of the electron is transferred into the energy of the photon. The energy relationship is exactly the same in both cases. In X-ray production, we can ignore the work function of the target and the initial kinetic energy of the electrons because they are ordinarily only just a few electron volts, very small in comparison to the energy of the accelerated electrons when they strike a target. Each element has a set of atomic energy levels associated with X-ray photons, and therefore has a characteristic X-ray spectrum. These energy levels, called X-ray energy levels, are rather different in character from those associated with visible spectrum. They're associated with vacancies in the inner electron configurations of complex atoms. The energy levels can be hundreds or thousands of electron volts above the ground state rather than just a few eV, as is typical with optical spectra. Now, a phenomenon called Compton scattering produces additional direct information of the quantum nature of X-rays. When X-rays strike matter, some of the radiation is scattered, just as visible light falling on a rough surface undergoes diffuse reflection. Compton discovered that some of the scattered radiation has a smaller frequency and longer wavelength than the incident radiation, and that the increase in wavelength depends on the angle through which it's scattered. And you can see that here. If the scattered radiation emerges at an angle B with respect to incident direction, and if the lambda and lambda prime are the wavelengths of the incident and scattered radiation respectively, then the wavelength increase is given by this expression. And you can see what's going on here. You've got the X-ray source, you've got incident photons coming into the target, and then you've got scattered photons going off to a detector. And then you can see the angle made there with the target, with the incident trajectory. Compton scattering cannot be understood on the basis of classical electromagnetic theory, which predicts that the scattered wave has the same wavelength as the incident wave. So in contrast, the quantum theory produces a beautifully clear explanation we imagine the scattering process as a collision of two particles. The incident photon and the electron initially at rest. The photon gives up some of its energy and momentum to the electron, which recoils as a result of the impact. The X-ray photon carries both energy and momentum. The total energy of the photon and the electron is conserved, and the same is true of the total momentum. Final scattering photon has less energy, smaller frequency, and a longer wavelength. So you've got incident photon coming in, and you've got the target rest here, and it comes in, they interact, the recoiling electron goes this way, and then you've got a scattered photon going off that way. So basically, you've got some energy that's come in, it's been given to this guy, and it travels this way. This also had momentum coming in, so you see the electron going off in some direction here. In order to make sure that the momentum is conserved, this has to go off at a particular angle to help compensate for the fact that this now has momentum, which it didn't have before. Also, for conservation of energy purposes, this has a longer wavelength because it imparted some of this energy to the electron. Obviously, as I was speaking about before, you've got several different X-ray imaging techniques that have come along, the CAT scanner or computerized axial tomography. Basically, you've got a thin fan-shaped beam that's detected by an array of several hundred detectors. The apparatus rotates around the subject, and the changing photon counting rates of the detectors are recorded digitally. Computer processes this information, reconstructs a picture of density over an entire cross-section. Density differences as small as 1% can be detected with CAT scans, and tumors and other anomalies much too small to be seen with the older X-ray techniques can be detected. I can attest to this because I have CAT scans that will do a scan on a patient, and I've got a doctor that will go through and draw those things, and I try to target radiation to treat those. So yes, physics actually does have an impact on people's lives daily. X-ray causes damages to living tissues. As X-ray photons are absorbed, they break molecular bonds and create highly reactive free radicals, which disturb the molecular structure of proteins and especially genetic material. This is basically a way, in order to be able to have X-rays create particles that can go in and hit DNA. And the reason you do that is so you can try to hit tumor to destroy it, and the normal tissue that's in the way have cells with repair mechanisms that allow it to fix the damage, whereas the tumor does not. So that's, again, an application of some of the things that we see in physics. So hopefully that was interesting to you.